Okay, today we're going to be looking at an example problem that has to do with stress and strain. So the problem says a bar of copper has a length of 2 meters and a diameter of 3 centimeters. It is held fixed so that the length cannot increase. The bar is heated 150 degrees Celsius and copper has a thermal expansion coefficient of 16 times 10 to the negative 6th, 1 over centimeters. So in this problem, we're going to be finding the strain and determining whether it's tensile or compressive, finding the stress, and then also computing the diameter after heating, assuming a Poisson ratio of 0.34. So first we'll start off by writing down what we know. We know a few things in this problem. So we know first that our thermal expansion coefficient, or alpha, is 16 times 10 to the negative 6th, 1 over Celsius. And I think for pure copper, it's closer to 17 times 10 to the 6th. I'm not positive about that, but you just want to go with what the problem gives you. Delta T, or a change in temperature, is going to be 150 degrees Celsius because it's heating up 150 degrees from the original starting temperature, which we don't know. The initial length we have is 2 meters, and then the diameter, I'm going to mark these both as D naught and L naught just because the length won't change, but the diameter will change. So 3 centimeters. So let's start with part A here, finding the strain. So we know that the equation for strain is the change in length over length. This is kind of the most common version of the equation. But the strain can also be found by taking alpha delta T. Okay, and we can see how this works out because just from units, we know that strain is dimensionless, and if we take alpha, which has a unit of 1 over c, we multiply that by c, we get dimensionless, right? So once we see this, we can just go ahead and plug in our values. So we have 16 times 10 to the negative 6th times 150 degrees Celsius. And I'll let you guys plug that in. And I got a value of about 0.0024. And again, this is dimensionless. But now we have to determine whether this is tensile or compressive. So in a bar with fixed length, we can kind of think of it as being held like this, right? And because it's fixed and it's going to be expanding, the bar itself is going to be feeling a compressive strain. So that's how we can kind of think about this. Our sides of the bar here are not going to move. However, the bar is going to be expanding or want to expand, which means it's going to feel like the sides, or wherever it's being held fixed, are pushing inward, which means it's compressive. So, compressive. Some people will write that as a negative as well. However, if you state that it's compressive, it's kind of implied that it's in the inward direction. So we're just going to leave it as that. For part B, find the stress in the bar. We're going to use our stress equation. Sigma equals E alpha delta T. And it gives us our E value in the problem, which is 121 gigapascals. So again, we can just go ahead and plug in our values. So we've got 121 GPa, 0.0024. Because we know that this is equal to this, right? And we already found our strain. And so we can go ahead and plug these in. I got 0.2904, GPa. And you can change those units if you need to. I'll go ahead and highlight our answers. So again, you can change the units of this if you need it in megapascals or just pascals. I'm going to leave it in gigapascals just because that's what we found it in. Part C, compute the diameter after heating. So this one's a little bit more interesting. It gives us our Poisson's ratio, and if we remember what that is, it's going to be the strain in the x direction over the strain in the y or the z direction. I'm just going to use z. So if we think of a bar being held at two fixed points, if I draw it back over here again, it's going to be 3D, and it's held here, and it's held here, right? And so we're going to assume that this is our x direction, and then we've also got, we're going to go ahead, and assume that the expansion that we're finding is going to be in the x direction. So I guess for this one, we'll use a round bar. Whatever the x direction is going to be not in the length, because that's not changing, right? So this is a little bit harder to wrap your head around. That's why it can get a little bit confusing. But we can go ahead and plug in what we know. So 0.34 is equal to negative ex. And we're going to go ahead and set our z direction to be 0.024. Right? So now if we remember that we have a compressive strain, which is compressive negative 0.0024, this cancels out this negative here, so it's going to be a positive. So then we can move that strain over. So we've got our Poisson's ratio. We're going to multiply that by 0.0024. Again, now things are positive. And this equals E sub x, or the change, or the strain in our x direction, which we can go ahead and write again as the change in L over L, or L minus L naught over L naught. Now this is kind of an approximation because we are doing diameter. However, this is a great way to solve this problem. And we have our L naught, we have everything we need here, right? And so we can just go ahead and do this in centimeters. So we have, again, 0.34 times 0.0024, which is going to be 8.16 times 10 to the negative fourth, is equal to L minus 3 centimeters over 3 centimeters. Okay? And so if we multiply our 3 centimeters over, cross that guy out, we can just go ahead and add the 3 to there, right? So now we have 0.00245-ish is equal to L minus 3 centimeters. And this is also in centimeters at this point. So add our 3 over, gives L our final length, characteristic length, which in this case is going to be the diameter. So I'll just set that to D, is equal to 3.002448 centimeters. So as you can see, the change is actually not that big at all. But yeah, that's just because the thermal expansion coefficient is super small. It's different for different materials. As I said, some are bigger than others. Yeah, so if you have any questions about this or any other questions you want answered, go ahead and leave it in the comments. And I hope this video helped you.